You're one of the tendon now. Oh.
Okay, give me a second here.
Look at the homework. I don't know what it actually. This is good. I have 12 hours. It's so close. It's on Saturday. You have far too much faith in me to be offensive. Yeah, because I came down from there. 20 minutes.
One second, Kyle. So then Kyle's gonna go over a design example, and I posted the design example on Canvas just a few minutes ago. If you want to go grab that with tablets, and if you don't have a tablet, I printed out copies. Who needs a copy? Matthew, you're one of the poor kids. All right. Anybody else? Anybody else got tablets? Okay. Thomas doesn't have one too. Okay. Yep. I'll hand it to him when he comes in. Make sure Luke's right up there in the front. Make sure he's paying attention. I'm gonna put Kyle in there today. All right. Kyle, can you talk just to make sure we can hear you?
Yeah, can you hear me?
Okay. Yep, gotcha. I think we're ready when you're ready.
All right. So you guys should see right now, I just got PowerPoint pulled back, and you should see just the limit states to check. And we're going to briefly re-go over the design steps and the difference between balance loading and doing it with strength compatibility on there. So we had talked about in the last presentation on Friday that these are really the limit states that you're going to check. First one is make sure you have that minimum amount of pre-compression. And we said with a two-way slab, has to be 125 PSI minimum pre-compression. That minimum requirement does not exist for one-way slabs. It's only for a two-way unbonded PT system on there. Then we talked about your stresses at initial service. And initial service is really right when you stress the deck. You're going to check the stresses right then. Then you're going to check your stresses at your service load combinations. And that is, buildings open, it's fully occupied, full live load in there. And then sustained service, that's the check that we're going to do just to make sure you don't have long-term creep issues. And we're really just trying to mitigate the amount of compression that we have, because the more you have there, the more creep you're going to have. The more creep you have, the more long-term deflection you're going to have, because that compression block is going to shorten, meaning you're going to get more deflection on there. And we had said, all right, with those three checks, you're using that balanced load approach right there. And then we had said with the strength level, then you go to more of a strength compatibility approach. And I want to go over that balance loading one more time. And Barry had a really good question right at the end, and I think it's worth revisiting that question to make sure it is clear. And the balance load approach, the first thing is, remember, it's an approximate method. So it's not exact science. It's not strength compatibility. It's approximation. It's close. It's pretty damn close. It's really close, but it's not exact. And to do it exact would be very intensive with the computing, and they've tried it with some FDA programs on there. So when we say it's approximate, what we're trying to do, and this is going to go into the question that Barry, you had. Let me make this full screen again. Give me a second. Trying to find that damn little pen. All right. So the question was, okay, why do we say WL squared over 8 when it's a continuous member? And I think there's a little bit of mixing and matching of apples and oranges, if you will, on it. So let's just kind of start over and talk about this one more time from the very beginning. And let's look at this middle span right here. So say we were to make a cut right here, and we were to make a cut right here on this middle span. It's unbonded post-tensioning, right? So because it's unbonded, what is it naturally trying to do? It's naturally trying to strain itself out, just like a giant rubber band would be. That's the best way to think about it. So we have a force this way, we have a force this way at that cut. And then we have a drape. And we know that if you have a force in here, that's your final effective pre-compression force on each side. and you know the magnitude of drape, you can say P times E is the amount of uplift, or P times A, sorry, not E, is the amount of uplift that you're going to have on this member, right? And we don't care that it's a continuous member yet. We're just looking at a finite section of it, and we're doing this cut, and we're saying there's a amount of drape here. We know this drape's trying to straighten itself out. And when it does that, it's going to try and put a continuous picking up load all the way along the tendon, right? And so the trick is we got to figure out what is this uplift load, this magnitude of uplift load that's going on this tendon right here. And then somehow we have to convert that drape into an uplift load on there. And so what we're going to say is, well, we know we have this drape, we know we have this force, and we know that that's creating a moment that's picking up on the slab, right? We also know because it's unbonded, it's going to be picking up all the way across this slab here. So that's where we say, all right, we're going to approximate that to be WL squared over 8 because we're looking for W, which is a linear load on the tendon. You could approximate and say it's equal to PL over 4. And instead of doing this linear load, you just do a giant point load right in the middle, right? But because the behavior that we see with the tendon is more of a picking up behavior, we're going to say it's a line load, and we all know the easiest way to find the line load in any given, single curvature things, WL squared over 8 on there. If you were to look at the exact FEA analysis of this load is not actually a linear load going all the way across. You have different magnitudes of curvature throughout the slab. So because you have those different magnitudes of curvature, you're getting different amounts of horizontal and vertical load kind of being pushed on the slab at the same time. And with that in mind, you'd see, greater loads at the bottom and then lesser loads where you have more steeper curvature of the picking up because more of your resultant's going sideways into the slab, right? So that's where the approximate nature comes into it. So we're able to say, all right, we're trying to find this line load. It's equal to WL squared over 8. And then we're going to come up with 80% of the balancing. Now where the continuous behavior comes into play is now we have put these line loads on the slab, and now we model the slab as a continuous element. And now is where we're getting that continuous behavior of the physical element itself coming into play on there. If this was a simple supported member and you're just looking at the drape, it would be a real simple math. You could say WL squared over 8 for your demand, WL squared over 8 for your balancing, and you could just divide those two and right off the bat, okay, here's the percentage balance I have. But because it's a continuous member, it's a lot more complicated, especially when you're looking at both your demand loading, which is going to give you the opposite moment curvature, right? It's going to do this. And it's not going to be a clean shape like this because typically, you're going to have this might be a shorter span on the end. Your interior span might be longer. There's a lot of different things going on. So, you're going to have different spikes and all that. And you have to really put into some sort of software. In today's day and age, you put into some sort of software to get that continuous beam bending behavior because of how indeterminate it is. And you're also doing the same with your balance loading, which is what we see in gray. And then that's where you can go cut your, your cross sections anywhere, and you can compare the two at any given point along that line. And you can see that behavior is going to be pretty complicated going all the way along. But when you're looking at your stresses, you make that cut every, our software will make that cut every 3 feet, do a stress check on there. And when you look at your amount of load balancing that you have, I'll just come over to this right bay just to be less cluttered. You're going to look at, okay, what's let's just say this is 70 kip feet here of uplift. Let's just say this is 100 kip feet for really easy, simple math of demand. We're looking at our max moment location, and we're saying, okay, we're 70% balanced, 70 divided by 100 on there. So that's how you approximate that uplift behavior that's going on the slab. So does that help clarify that topic?
Yeah, the one thing, Kyle, is that when you're saying the moment from the, and I still have issues with a little bit. When you say the moment from the pre-stressing is 8 or is the force times the drape as opposed to force times the eccentricity.
It's unbonded, so there's no, how does that tendon know? Let's draw a couple shapes here. Let's say we had a T-shaped cross section, right? And then let's say we had a beam cross section like this. And let's say our tendon's right here and here, same elevation in both these. Our centroid of our shape on this one's going to be right here, right? Our centroid of our shape right here is, it's going to be up higher, obviously, because of the T section. However, if we had the same drape between the two, because it's an unbonded post-tension system, it's going to pick up the same amount. It doesn't care whether it's a T shape or whether it's a rectangular shape. It's going to pick up the same amount. So that's why you can't do P times E with an unbonded system.
I gotta see that, but then I think when it goes back, like when you put it in software, it will, like, and you're checking the stresses at all locations, I think it's doing the P times the eccentricity, and it's doing the P over A, and it's doing, I think it's doing that, because I think even though it's
So the software will do the
stress checks, right? Yeah.
So for the stress checks, the only P times eccentricity that I would do is if you had eccentricity at your anchorage zone. So say for whatever reason your tendon was higher and it was up here, it would take that P times eccentricity into account at your anchorage zone right there. But it's not going to take it into account in an FEA software. It's not going to take it into account at the load balancing for your service checks. Because what it's going to do is it's going to take all those PT tendons and it's going to apply it as an external load, just like you put a dead or live load onto your slab, and then it's still going to look at it like a gross cross section.
Yeah. Okay. Cool.
So, and I would say this behavior is, this is a approximate method that's pretty damn close. I've looked at this with the guy who writes, the head developer for the main software for unbonded post-tensioning that gets used throughout the world. He kind of turned into a drinking buddy of mine, and we've had a lot of beers talking about concepts. And it's a very, even within the post-tensioning industry, I'd say 60-70% of engineers out there that are designing PT slabs don't even wrap their mind around this concept by hand. They know how to use the software, but they don't understand this concept itself on it. And a lot of it has to do with being unbonded. If you're bonded, then yeah, all these rules go out the window, because at any given cross section you have that true eccentricity, and it cares about the shape on there. And that's, this is the software where I showed you, okay, here's how the loads get applied to it. Here's the, you could approximate it more to look at wherever we have negative curvature, we're going to put a downwards load. Wherever we have positive curvature, but this area, this drawing's not a very good drawing to scale. There really should be like a double cut line here and a double cut line here, because this area here is 20% of your length versus this area is 80% of your length picking up, and then you have 10% over here. And so really the magnitude of area where it's pushing down is so small compared to the amount of area where it's picking up on the slab, because your curvature, your inflection point, your curvature is only 10% of your length off your support. So if you have a 30-foot long center line to center line, you're only gonna have 3 feet on this side. You're gonna have 3 feet on this side. That's nothing compared to the 30-foot of span that you have on there. So.
Right.
Okay, so whether you believe me or not, we still know this is the way that you're supposed to do it. And so you're going to go P over A plus minus your balance load moment. And we talked about, you get your balance load moment from this diagram right here by applying these uniform loads on there. If you're using FEA software, it's going to do the same thing. This is a tendon line. It's going to put those uniform loads on there, and you can see every single load, it's the same magnitude on the uplifts. They're all 1.41, 1.41, 1.41, going all the way down the gut here. And then once it starts to go down to the downwards, this is where it gets a little more confusing when they're really concentrating. Ignore. Oh, it's too clear. You can't see it. Anyways, they're concentrating that point load right in the middle, pushing down right here. And if you're to add up all these downward loads in here, they're going to equal your amount of loads picking up within your tributary width on each side of it right there. And so, because it has to be in equilibrium, right? We're applying an external load to the slab. Well, and it's not a gravity load. And so that means if you have X amount of uplift, you're going to have X amount of downwards on there too. So we're going to do our P over A plus minus balance load plus minus your moment demand combo all over S is your classic, real simple equation. We're gross cross section, right? So S is super easy to calculate. This is a very straightforward fundamental calc on there. And we're going to go through that and check that. The FEA software, what that's going to do is, let's just say we have a column here and a column there. It's going to cut. This is the meshing of the FEA that you see right here. That's going to then, if we have tendons along this line right here, it's going to have a bunch of, uplift loads all the way along that's applying. And then it's going to go look at just that, and it's going to figure out its moment diagram, but it's going to cut a cross section of this width. So it's going to take all the PT10. Actually, this is going to go all the way up to your slab edge because there's not a column, and then it's going to go halfway to your next one, and it's going to cut, and it's going to integrate all your uplift forces to figure out what your balance moment is. It's going to integrate all your downwards forces across this cross section to figure out what that demand combo is, and then it's going to run that P over A plus minus M over S calculation. And then every 3 feet, it's going to do a new cross section. It's going to run that calc again, and it's going to run that calc again, and again. Then it's going to do it for all 3 service states. So it's going to do it at the very beginning when you're stressing it, and there's only the self weight and no superimposed dead load, and there's higher PT forces because you haven't gone through the long-term losses of shrinkage and creep. It's going to do it again at your final effective force with your dead plus your lives. Then it's going to do it again at your sustained service check. And so it's a very powerful software. It's doing all this within the course of 30 seconds across the entire slab on there. All right, so we're going to kind of push forward, and then we're going to talk about, okay, the more traditional design. And this is when you look at from the strength level standpoint. So now we forget completely about load balancing and the post-tensioning tendons. In load balancing, we're an externally applied force, just like a dead load or a live load. When we look at the traditional, your post-tensioning or your pre-stress forces is just like it is what you've learned so far in class, which is its strain compatibility of your cross section on there. And when we go look at those forces, I'm going to go back to the hyperstatic here in a second. I'm just going to go to this page right here. This is your classic, VMN is equal to VASFY times your moment arm D minus A over 2. And if your post-tensioning tendons and your mild rebar are in the same exact plane, then it's a really easy calculation because you can simplify it to be APS FPS plus ASFY times D minus A over 2. Oftentimes, though, your rebar, say it's a beam, or you don't have any rebar at all, but say it's a beam, your rebar might be in the very bottom, but your PT tendon, depending on where you cut it, might be halfway up or somewhere in there. And then so you just have to break up that moment arm distance and look at what your actual strain is at each particular location for it. So let's talk about this concept for a second, because this is another very confusing one with unbonded post-tensioning. Let's just forget about the rebar for a second and only focus on post-tension. Let's say this is a piece of unbonded PT. Well, where people have a hard time wrapping their mind around it is they say, how can there be strain compatibility if it's unbonded post-tensioning? Meaning, if I were to cut this cross section, there's grease and sheathing around the thing, I can't develop any, tension force to just slip right through that sheathing. That's a question I get a lot on there. And a lot of that answer comes back to, well, there's still your anchor back here, which is holding it together. So if you were to draw, just say a basic beam like this, and let's just say we have a flat tendon coming across here, We still have our anchor here. We still have our anchor here. And so we have it holding together. Now let's draw an extreme view of this. Let's say you had a crack and the beam kind of looked like this. Right? Well, you got your tendon, and then it would be pinched going across here and then be coming across here. Let's just say you had some length across here, right? Well, that length's still constant across the top of your beam, but the bottom, let's just say this crack opened up to, I don't know, 3 inches, you know, some extreme amount. At this point in reality, your compression block would crack, but let's just say the concrete's infinitely stiff, you're not going to crush your compression block. Well, if you have anchors on both ends, if you're to open up a 3-inch crack, that means that strand has to elongate by 3 inches to be able to get that far. So that's where you get that strain compatibility with unbonded cross sections in there. You can look at that. Actually, no, I'm not going to say that. It's going to confuse everybody. so that just keep in mind, because yes, it's unbonded, but if you were to look at the anchorage zone, it's keeping it so that you do have strain compatibility to a certain extent within your cross section, right? So, all right, we know that. We know through strain compatibility of, you know, your basic, we got this, you got a compression block, depending on which way you're drawing your things, starts like that, and then it eventually goes to, you know, some sort of behavior. And then we have your PT tendons and your rebar on the same plane, and you're just looking at this cross section that we have on the left, right? And your moment is your distance from your moment capacity is obviously your distance of how much strains in this piece before the concrete crushes. And how you figure that out is ACI says, remember we were talking about that 26.8 tendon kips per foot or kips per tendon as our final effective force. But in an ultimate scenario, because you are elongating and you are getting some crack here, it's going to be really complicated to by hand truly figure out, okay, what's that actual strain, you know, drawing out this and figuring out what's that amount of strain in that piece of bar, and then figuring out all the calculations for it's strained X amount and blah, blah, blah. Here's my final force that's in here based on that compatibility. So instead, ACI gives you, it's more or less these two equations right here, depending on what your span to depth ratios are. But it says take your 26.8 kips per force, divide that. So that's your final FSC right here, plus 10,000 divided by, or plus your F prime C divided by 100 times your reinforcing ratio you're pre-stressing on there. So they give you a very simplified equation that somebody did a ton of research on back in the day and said, hey, we believe the actual final ultimate force in these things when the concrete crushes is going to be somewhere around this. And they just say use these equations on it. Versus with a piece of rebar, right, you just say it's 60 KSI on there. So with PT tendons, you kind of run one of these equations, figure out what it is and how much elongation you're going to get back to, which goes back to this, you know, what we were talking about right there, right? So that's all still pretty, once you wrap your mind around it, and pretty simple, makes sense. You just follow those equations. So the confusing part becomes the hyperstatic stuff. And the hyperstatic stuff comes to, now we get back to the P times E. So if you're to look at any sort of, if you're to sum up all your moments from your P times your E and all your given cross sections on here, and here's your tendon, you can see you have a lot more P times E below the CGS than you do above. So because of that, you know, you have this moment picking up here, you have this moment picking up here, and then you have this moment here. I should call this negative moment, this positive moment right here. All these don't equate. Your moments aren't in equilibrium. So because your moments aren't in equilibrium, the slab's going to try and move. And because it tries to move, what it's going to do is most of the time it picks up. So it's going to try and pick up after you've stressed it. But what's going to keep the slab from picking up is the fact that you have a column with rebar in here that's holding it down. So if you were to, in a lab, make a continuous beam and just truly put it on a roller support after you stress it, you'd actually see it pick up with some camber right in the middle, most likely, because of that secondary effect. And the secondary is, first you stress it, then you get this moment P times E, and then the secondary effect is the whole thing's trying to pick up because your moments of your P times E aren't in equilibrium. And so that creates a secondary moment on the thing, or as you'll often hear referred to, a hyperstatic moment on there. I try and use hyperstatic, like I said on Friday, in terms of using secondary just to not confuse it with P delta stuff or lateral type secondary moments on there. And so if you have a force that's holding this thing down, which is i.e. your column, if you didn't have that column in there, we talked about you'd actually deflect up. So you don't really engage that. You don't have a secondary moment because the thing's actually deflecting up. It's picking up, it's moving. But you have a force holding it down. And so because you have a force holding it down, it's introducing a moment into that slab. And that moment is going to help you out, usually because it is more of a, it usually helps you over your columns, locations on there. And it looks like for a 3-span, it's gonna be pretty simple. So you had nothing at the end, it's just gonna go up, come down. For a multi-span, it's gonna go up from the end. If it was pin support, it might slightly taper down and then come over. So it's a fairly uniform moment that's on there. And so how you calculate this is another theory out there. And it's a little bit of mixing and matching both approaches, but you can say, we know our balanced moment has to be equal to our primary moment, which is P times E plus our hyperstatic moment. Because we're saying our load balancing, our balance moment, everything has to be in equilibrium, right? So because we're saying it's in equilibrium, we would say if you did have a primary moment, which would be your P times E across your cross section, you'd also have to have a hyperstatic to equal what your balance moment is. And you can further build out this equation and say, okay, your balance moment's equal to P times E. We know that. Plus your hyperstatic. And then if you want to solve for your hyperstatic, you just rearrange the equation and you say, okay, our hyperstatic is equal to our balance moment minus our primary moment. So if you were to look at any given location, you could say, at the end of a column, at the very end, let me go back to one of those diagrams. At the very end here, if we do our job right, we're exiting our tendons at mid depth. So we know our P times E right here is 0. So that means our secondary moment here, if we know that's 0, let's rip back to that other equation we were just looking at. So we know our P times E is equal to 0 at the end. That means our hyperstatic moment is equal to our balance moment. So let's go back. Hang with me. You know this is your balance moment, and you do have some sort of moment at your end bay because there is some stiffness compatibility between your slab and your column. If you have a 24-inch by 24-inch column, you have an 8-inch slab framing into it, thing's got a 30-foot wide tributary area. Yeah, that thing's got some stiffness and flexure to it. And so there is compatibility of those two moving together. So you are going to get a little bit of positive moment right there. And your secondary moment has to equal, for your hyperstatic moment, has to equal that at your end phase because it's P times E. Then you can go calculate it again at your mid span right there. And then you can start drawing out your moment diagram, what your moment diagram is going to essentially look like. It's going to angle down, it's going to come over, it's going to angle back up. That was terrible. It's going to angle back up to right here. Ignore that piece. Going across there, that's going to be your secondary hyperstatic moment that's going to be acting on the side. When you use your load combos, ACI tells you use a load combo of 1.0, right? We're doing LRFT design with concrete, so you're going to use 1.2 dead, 1.6 live, 1.0 hyperstatic in your combination that you have on there. And so again, this is kind of an approximate way to figure out what those hyperstatics are, because we already said that your balance loading's approximate. So now we're mixing and matching a little bit approximate methods with strain compatibility, which is not. However, it's the closest way that you can do it without doing a crazy advanced analysis on there. This theory got developed in I think it was like the mid 70s is when they developed this. So back then they were doing a lot of these designs still by hand. They weren't using software. And so they needed a way to simplify it that they could do this by hand for a multi-span element on there. And they were doing a version of equivalent frame analysis on there. So this is a snip from the software, and these are hyperstatic moments that you can see at a column. You can see your axial load that's holding down is 32 kips of force. So that's quite a bit of force that's holding down that slab that's trying to pick up right there. And then from the unbalancing of the moments, you can see you have a moment of 19 kip feet about your R axis and 10 kip feet about your S axis. You can go over to your end bay. You can see it's a lot less vertical pickup right there. And a lot of that has to do with just there not being a ton of that P times E for it to pick up there. But you do have quite a bit of moment, especially about your S going on in secondary hyperstatic. And then this is a beam moving in right here. So there's all kinds of crazy behavior going on there on the FEA program. And so you can see there's 40 kips of uplift right there. So those secondary hyperstatic forces, they are real forces, but they do generally help you out because they're pushing down where your slab's trying to pick up. So they help that negative moment region over your column supports in there. So in general, those hyperstatic forces are actually a good thing in your strength level designs for it. We're doing a bunch of research right now analytically to essentially say there's a better way to figure out strength level calculations than mixing and matching what we just talked about. And what we're trying to say is we're trying to say that, you can actually look at, we very much believe the concept of balance loading and those forces are true. And what we're trying to say is when you get to the strength level, why not use more of the balance loading to figure out what those secondary forces are than doing all this P times E and everything. And so there's a paper that was published in a journal a year or two ago, caused a lot of controversy, a bunch of just smart people trying to argue with each other. A lot of it was folks that have been doing it for 40, 50 years, and they just didn't want to see the change, in my opinion. But there's a pretty good push right now to change the way that you look at these secondary moments at the strength level to make it more of a simplified approach and less of that mixing and matching on it. So the building code, though, it does not tell you how to actually calculate any of this stuff. It just tells you, it's just like building code really doesn't tell you BMN equals PAPS. They just say you got to use some sort of compatibility on there. It doesn't tell you how to go about and calculate these loads and this balance loading, any of that stuff. If you go into the building code for unbonded post tension, there's really not anything, very little information for you in there. And so you do have to rely on a lot of those guides, and I'll kind of show you those guides on Wednesday and Friday in there. So I'm going to skip that. That's a table you guys all know. Let's talk about punching shear design real quick. I'm not going to get way into this because it's a really complicated behavior and nobody really knows what's going on with it. But there's, we talked about using stud rails as the number one thing to use. The other thing you can use is you can use drop caps or drop panels. And that's what you're staring at right here. This is a podium slab. If you use a drop panel, it has to have certain dimensions to it for width on there in each way. And once you use that, you can actually use the full depth of that for your flexure calculations over your column head. So if you ever were running into negative moment issues over your column head, you could use one of these in theory to get a little more depth right over that for flexure, and it gives you more punching shear capacity. The downside to this is it's extremely costly from a labor perspective to form this, because from a forming standpoint, you have to put in a bunch of form work at this lower level. And then you have to come back and form up this higher level over here. And then this whole in between region, you have to then go do another false ceiling in there all the way around to build those. So it is typically more cost effective just to specify a stud rail than doing a drop cap and drop panel. So I say if you're going to do a drop cap or drop panel, only do it because you need it for flexural issues, but in general, try and specify those stud rails. There's going to be more material costs associated with those stud rails compared to the concrete. However, the labor cost is going to be saved by a significant amount. Labor in the field right now is extremely expensive on that. So the more you can keep your slabs with a flat soffit, the more economical those slabs are going to be. And to do that, use those stud rails. And remember, those stud rails are just going to act just like a beam stirrup for shear resistance. You know, shear is going to be at some sort of angle, 45 degrees. It's going to be flattened out a little bit because of the pre-compression that you have in there. But that's going to be your resistance. And you're actually going to get a higher allowable stress capacity from ACI than you would if you're using rebar with these stud rails on there. That's all I'm going to say about punching shear. It's a whole, you know, we could talk for an entire semester on that topic. So minimum steel requirements. We briefly talked about this one, but if you're doing a beam, your minimum steel is 0.004 times your cross-sectional area, and it needs to extend a minimum of L/6 past your column face. So here's a big transfer girder right here in a slab. You can see this column sticking up right there. There's another one that you can't see right here. And then there's going to be a column that comes up, a planar column that starts right here. You can see this minimum amount of steel. We have two continuous bars here and here. But then to get this requirement 0.004 for a minimum of L/6, you can see these bars actually stop right there. And then we just have little tiny bars the rest of the way to support those stirrups in there. So that's a minimum amount that you need for a beam. For post-tensioning in the two-way flat plate slab, you don't need any in your positive reinforcement region, not even temperature and shrinkage. You don't need any, as long as your tension stress is less than 2 square root F prime C. No steel is required. So 2 square root F prime C at 5,000, that's this 141 PSI on there. This red is our demand tension stress going across the cross section. You can see our demand tension stress is 89.9 PSI. We're less than 2 square root of F prime of C. Therefore, we don't need any tension steel in there. Nothing. However, if this were, say our demand were to creep up, and let's just say it was on 200 PSI of demand right there, you then need amount of tension reinforcement in that slab itself. And that amount of tension reinforcement is, you look at your net resultant tension on the cross section divided by, they essentially make you put twice the amount of steel in there as the amount of tension you'd have. Remember, 424, that's our 6 square root F prime C on there. So in theory, when you're in between 2 and 6 square root F prime C, so 2 square root F prime C by it being this 141, 6 square root being this 424, in theory, the thing should never crack, right? Because we haven't gone past our rupture coefficient of 6. But they're saying, you know, we want to be extra cautious, so we're going to make you put in quite a bit of rebar in that one area. It's okay to put in some bottom rebar. You don't necessarily need to keep increasing your tendons to get below this 2 square root, because if you increase your tendons, you might actually end up with an overbalanced situation, right? We said if there's only 2 ways to get more load balancing, it's more PT tendons or more drape. If you're max out on drape, you increase your tendons to try and get less than this. Well, now you might be over drape or overbalanced, which isn't good. So it's better to just put in some mild steel. So that's the only time you need the mild steel. You usually see it on your end bays, and that's because you don't have the full drape on your end bays because you're always coming in at the center of your cross section. There, that's where you typically see that minimum area of steel required. It doesn't really do anything for you. It's just a minimum that the code makes you put in there. Over the column heads, we talked about this already, but we said, hey, you have to put in some minimum amount of steel over in both directions over your column head, and that steel is going to provide ductility control and it's going to provide crack control. We talked about typically you have enough PT tendons that if you're to look at your strength calc at that cross section, that you would not actually need that mild steel for moment capacity in there. So it's not doing anything for your strength. You get to count it, but you don't need it for your strength. So it's there just to provide some ductility. And again, a giant lateral event, what's going to happen? Your negative moments are the ones that happen first. And it's usually your negative moment flexural cracking comboed with your shear cracking where you get a failure at your column where it punches through. So it gives you some ductility right there. Although, again, I mentioned this before, you don't count this ductility as part of your lateral force resisting system from an energy dissipation standpoint. So it doesn't help you towards your R value when you're doing those calculations, right? It's just there for kind of a belt and suspenders on it. The amount that you have to put in is this 0.0075 ACF. That ACF is your cross section area. So if it's an 8-inch thick slab, you go halfway in between this column, halfway in between this column, take that, whatever it is, 30 feet, that keeps saying, multiply it by your 8 inches thick, multiply it by this 0.0075. Usually comes out to be somewhere around 10 number 5 bars. That's kind of roughly plus or minus on there. You always use a number 5 bar because number 5 bar is the same. Yes, it's 1/2 inch diameter tendon, but with the sheathing, it makes it 5/8 of an inch. So your number 5 bar is the same diameter as your PT tendon, so they can coexist in the same plane. If we look at these banded tendons, this rebar is in the same plane as those banded tendons. You have banded tendons and then you have rebar in that same plane. So you always want to use number 5 bar when you're specifying it in there. The last thing is just you always need 2 tendons going through your beam cage, and that's just last second in the Northridge earthquake. It was shown that a lot of the slabs didn't collapse because those 2 tendons were just left hanging and holding up the entire slab. So they make you put that in there. If you don't get it in there, you can add some more bottom bar in there. So that's really the minimum amount of bottom steel you need. So the next thing to always think about is fire protection. This is one that becomes an afterthought, but sometimes can drive you more up front. And there's is your slab restrained versus is it unrestrained? This is a big argument out there in the industry. Restrained slab means with fire, as the thing expands, it has nowhere to go. So interior bay, concrete bay, they say that's restrained because as that bay tries to expand, it has its neighboring bays that are going to prevent it from expanding. There's some documents out there that say exterior bays, as long as it's cast in place, are also restrained because if they were to try and expand out, just through deformation compatibility of the rest of the slab, it would have to pull the rest of the slab with it and it's going to be okay. There's other documents out there that say your very end bays, because there's nothing to the side of it, have the ability to expand out, so they're unrestrained. The big difference in that is your clear cover, and lots of times with these slabs, you need a 2-hour fire rating. That's what you typically always are being required to have. With a restrained slab, you can get away with 3/4 inch clear cover. Unrestrained slab, you have to have 1 3/4 inch clear cover for a 2-hour rating on there. And remember that end bay, you're already limited on drape because you're exiting your tendons mid-height, so you're not getting that much drape at that end bay, and you're trying to go down to your low point. So then if you're stuck to 1 3/4 inch, that really kind of beats you up on the amount of load balancing you can get because you really aren't getting any drape, your deflection performance, all those things, and you end up throwing in a bunch of add tendons at the very end bay to do it. If you go to California, a lot of the plan reviewers in California that I've gone through, they've always said those end bays are unrestrained. We don't care what your argument is. You go to the East Coast, the plan reviewers don't even look at your documents, and they just say, sure, whatever you call, you're the professional on it. I always do this one, and I wait for them to try and fight me on it. On there, I call it restrained, or they're just because I need that drape, and it's not going anywhere. Too. So, but something to think about at the beginning of a design that often gets overlooked is think about that fire protection aspect of it, because if you don't, you could have a design that's finished, you think it's good with 3/4, and then you end up having to do 1 3/4 inch, and you got to go back and redo all your design. All right, so from here, I'm going to briefly go through this example that Barry printed off for you guys. This example is the example that we just published in the recent version of the Post-Tensioning Institute manual. It's a great example for doing 2-way slabs by hand while also using software from the standpoint of your indeterminate frame lines, just using software to figure out where your demand moments are on there. And so what I'd like you guys to do is kind of go through this example on your own, but I'm going to give you the highlights of this example itself. So we're looking at a 2-way flat plate slab, and we're going to go through what this slab is. We're going to say, all right, we're going to use the 2021 International Building Code. And then if you look at 2021 International Building Code, it adopts ASCE 716 and 31819 on there. So those are the codes we're going to use for this particular project. We're going to say it's a multifamily residential building, meaning it's type 1A. So if you're to actually go through the IBC, you know, your job as an engineer, when you know the building's type 1A, is go through and figure, okay, if it's type 1A, how many hour fire protection do I need? So you're going to go through the IBC, you're going to say, okay, type 1A construction, I need 2 hour fire protection. We're going to say it's seismic design category B, just to make our life simple, not have to worry about seismic stuff because that's not the intent of it. We talked about the fire. We're just going to say, just assume everything's fully restrained in there, all your bays. We do have this kind of CYA note that says you as the engineer, though, it's your responsibility to be able to justify it one way or another. Assume two-way uniform thickness, no beams, drop caps, or panels. Remember, those cost a lot of money to form. Then we're going to say 27-foot, 6-inch square column grid in each orthogonal direction for 3 bays. I'm going to talk about that here in a second. Then just for starters, let's say 16-inch by 16-inch square columns that are 10 feet tall in height on there. So the reason why we're going to use 27-foot 6 is it's a very common number and great starting point in these designs, 27 to 27-foot 6, because what you can do with that is you can fit 3 8-foot 6 parking stalls in there. So paint to paint dimension of a parking stall for a multifamily building is always going to be 8-foot 6 inches, right? So you're going to say 8-foot 6. We're going to do 3 of these. Do one here. Do one. Just pretend like these are all lining up at the same spot. Like that. So that means we have what? 8, 16, 24 plus 25-foot 6 of space, clear space in between the two. So now that's allowed us to go all the way up to a 2-foot wide column in between it. So I love starting my column center lines at 27-foot 6 because that allows me to go up to a 2-foot wide column. I know punching shears is going to be one of my most critical design things. So the bigger the column I can get, the better my slab is going to be efficient on there. I might be able to get talked down to doing a 26-6 or 27-foot flat if I could justify doing an 18-inch column on there. And, you know, I think this one we're doing, what I say, 16 or 18 inches. So you could definitely reduce a little less, but ask for more at the beginning. So very common span that you're going to see on this. And when you go to do one of these designs, here's the design steps that you're going to go through. You're going to determine the initial slab thickness, and we talked about that. That's going to be a span to depth of 40 to 45, and I always go center line to center line. You're going to determine your demand loading. That's, you know, basics that you do in every class. Doesn't matter whether it's PT or not. You're going to identify your starting pre-compression required. We talked about the absolute minimums 125 per the building code. You don't want to go over 300 because you're going to have code issues. 175 is a great starting point, 150 somewhere in there. You're going to determine your section properties of your slab. Really easy. It's gross cross section, rectangle, BH squared over 6, right? You're going to determine your demand moments. This is where I go into a piece of software. Now, the one thing when I'm doing this is, what's that crack factor you're using in your column? You can't just use 0.35 of ACI. You got to actually think about, is my column going to be cracked? Is it not? Look at your axial loads coming down on that column. Is it external column versus internal column? An internal column without much moment on there, well balanced, that's no ways it can be cracked. External, maybe, but usually you have so much load coming down that's not going to be cracked. So you might consider using a stiffness factor of 1 or 0.9 or 0.8. You got to justify that as the engineer for your column. And that's pretty important justification because that column is going to tie directly into your slab through your FEA model. And so it does make a difference whether you use 0.35, 0.5, 0.8, 0.9, or 1.0 for your column stiffness on there. That's up to you as the engineer to figure out. You're going to load balance each span. We talked about how to do that. You're going to check your initial service stresses. We talked about that. That's right when you're stressing the deck. You're going to check your service stresses. That's when the building's open and there's a big party going on in there. Sustained service stresses. Then you're going to figure out what your minimum bonded reinforcing is. We went over that. Most of it's just for ductility steel that you need. Then you're going to determine what those hyperstatic moments are. We talked about how that is going. Your balance moment has to be equal to P times Z plus your hyperstatics. Then once you know all that, then you can go check your ultimate strengths. Your ultimate strengths is just going to be VMN has to be greater than your demand moment plus your hyperstatic moment gets added in there. Then you're going to check your punching shear. Then you're going to do some additional design considerations such as fire durability, some of those other things in there. So those are the steps that you're really going to go through. And so what this example does is it goes through step by step each one of those, and then to figure out what your demand moments are though, all we do is we just take a piece of FEA we took a model that looked just like this in our finite element software. We modeled it. We looked at our widths kind of going across, here. And we were able to figure out, okay, what's our moment in our column? What's our moment mid-span for everything? And you're able to, see what all those are, run all your calculations, figure out all those stresses, do it for all those different checks on there. So what I'd like you guys to do kind of between now and Wednesday and Thursday is really on your own, go through this example, try and wrap your mind around it. It holds your hand. It's very simple. Should be a couple hour thing. I'm just reading at the end of the day. So, all righty, guys.
Awesome. Thanks, Kyle.
Yep. Talk to you guys on Wednesday.